Hi, this is a talk about Black Holes Can Dance by Sethanne Howard of the Washington Academy of Sciences. So people have a picture of what black holes are, and this is what they think. It's black and it looks like a hole. So therefore it's a black hole. Basically, black holes are not really holes. They are a lot of mass in a zero volume. That's tricky to do. But they're not really black either. They're invisible. So that's what it's important to remember. They're called black holes, but they're not black and they're not holes. Light acts funny around black holes. It travels in straight lines because Sir Isaac Newton told us that. Is that true? Almost true. Because Einstein came along, and Einstein showed that matter can bend light. Mass can bend light. In other words, light comes in from a distant star, passes the massive sun, and bends. And nothing can travel faster than light. Newton, this is a picture of a grid, whoops. And the straight line is what Newton said would happen, and the curved line is what Einstein says will happen. 20th century. So light rays bend around a massive object. Here's an object and the light ray is bending. The more massive the object, the more the light is bent. There's a massive object, and you see the light is almost making a circle around the massive object. So Einstein showed us that mass can influence light. So the geometry that you're working with, space-time, which we think is Euclidean, flat, it's not. It warps when it's close to a mass. And the more mass there is, the more it warps. That's the geometry you live in. And if you have a massive enough object, it will capture the light and it cannot escape. So that's a black hole. Well, so what I'm going to talk about today is the very basics of black holes. We need Einstein, unfortunately. There are no worries about some things. Visit a black hole, that's a worry. Measure a black hole, make a black hole, see a black hole, and then we'll dance. So no worries for some of it, but worry with some of it, some other stuff. That's what I'm going to talk about. So the very basics, most people represent a black hole as a four-dimensional sphere. And we're taking a cut through the sphere, and it's a circle like this. It's got the inside of the circle where the radius is 0 at the middle. Then the edge where the radius is an edge value, the edge of the black hole, and the outside world. Those are the three pieces of a black hole. It sounds simple, 3 pieces of a black hole. So part 2 of the basics, we did the outside is the rest of the universe. We've got the inside. The edge is also called, another word for the edge is the event horizon. And outside, you can escape the black hole if you're traveling less than the speed of light. You can get away. That's your escape velocity. You can escape it. At the edge, you have to be traveling at the speed of light just to stay on the edge. Inside, you have to be traveling faster than the speed of light, and nothing can be traveling faster than the speed of light, so you can't get out. That's part 2 of the basics. You know, how fast you have to be going. And the only way you can escape is to be outside in the rest of the universe. So the geometry is not flat. This is the way a lot of people diagram a black hole, the geometry around a black hole. It's worked, it's highly deformed. The black hole is in the middle, and then this is a radial distribution of the geometry. It's not Euclidean, it's not flat. Now we need Einstein because he gave us the general theory of relativity. Now I'm going to show you, so you can say you've seen it, the equation of general relativity. Usually when I give this talk, nobody wants to see equations. So I'm going to show you the equation. Don't panic. That's it. It's a very complicated equation. It's not simple at all. It's actually 16 equations in one. So it's not a simple equation. In English, it says mass tells geometry how to curve, and geometry tells mass how to move. That's what you're saying with that math. But unfortunately, the poor kid realizes calculus is the easy part of this. This is complicated stuff. It's not easy to solve. And so there they go. And that lots of math happens, and I'm giving you the shorthand for math. Lots of math, and the technical term is arm waving. We're doing arm waving to do all that math. And once you do that, you get a singularity at the center, r equals 0, i.e. a black hole. So after you do a lot of math, singularity at r equals 0. So the question is, what is a singularity? And the math gives you at the center 1 over r. It just works out that way. And 1 over r at r equals 0 is undefined. It's not 0, it's not infinite, it's undefined. And what that means is that the science equations, even Einstein equations, no longer work at the center of the black hole. All the science we don't know the science of the inside of a black hole. That's what a singularity means. And Schwarzschild, now Einstein published this in 1915. And in 1915, it was World War I. And Schwarzschild was fighting on the Russian front for the Germans in 1915, and he had some free time. So he published several papers, and one of them was solving Einstein's equation to produce the geometry for a non-rotating spherical mass. A spherical mass doesn't rotate, just sits there. And he showed that there would be a singularity at the center. The edge is called the Schwarzschild radius, and the edge is the event horizon. Now, unfortunately for us, he got sick at the Russian front and died. So after he published all these important papers, and he sent them to Einstein, and Einstein said, this is great, but we lost him. He got sick at the Russian front. The Schwarzschild radius is a very useful thing to know, because if you want to know the Schwarzschild radius of an object in kilometers, it's only 3 times the mass of the black hole. So 3 times the mass of the black hole in solar masses, using the sun as a standard mass. So let's look at examples of this. If you take any mass and you squeeze it down to within the Schwarzschild radius, it becomes a black hole. For the Earth, the Schwarzschild radius is 9 millimeters. So if you could squeeze all of the Earth down into a less than 18 millimeter diameter sphere, the Earth would become a black hole. So let's look at some examples of black holes, of Schwarzschild radius. For a human being, the Schwarzschild radius is less than an atom. You'd have to squeeze a human being several times smaller than an atom in order to make a human being into a black hole. The radius for the Earth is 9 millimeters. For the sun, it's 3 times 1, or 3 kilometers. That sun is the standard. So a 3-sun solar mass star, a star with 3 suns mass, it's 3 times 3, or 9 kilometers. That's why the Schwarzschild radius is a useful quantity. It tells you how big that radius is going to be. There's a website on the bottom listed that is a calculator for Schwarzschild radii, and you can play with anything you want. It's for people to play with, to calculate the Schwarzschild radius of any object you're interested in. Now, it's important to know that black holes are not cosmic vacuum cleaners. Kids tend to think that black holes zoom around space, sucking up matter, and they don't do that. They sit there quietly and orbit just like everything else in the galaxy. It's sitting in the galaxy, it orbits like every other star, only it's a black hole doing the orbiting. They do not zoom around loose, sucking up matter. So don't worry about that. If you're far enough away from the Schwarzschild radius, you don't have any worries. The black hole isn't going to do anything to you. You only get strange things happening to you when you're near the Schwarzschild radius. And if you're at the radius, you basically worry. That's a point where you worry. So the question I have for you is, what would happen if the sun became a black hole? The radius for the sun, Schwarzschild radius, is 3 kilometers. So you shrink the sun's mass down to a sphere less than 3 kilometers in radius. Would we notice here on Earth that the sun became a black hole? And the answers are yes and no. We would notice because we die, because the sun would turn dark and we'd lose sunlight, and so we wouldn't be able to live. But the Earth would happily keep orbiting the black hole just as it was orbiting the sun. It would just keep going around without change. The Earth wouldn't care. The Earth wouldn't notice. So yes, we'd notice because we die, because it would be dark, but the Earth would keep going. So what I want to do is take us on a trip to a 3 solar mass black hole, a black hole with three suns in it. So it's 3 times 3, or the Schwarzschild radius is 9 kilometers. And the spaceship has a smart astronaut and a dumb astronaut. The dumb astronaut wants to visit the black hole and drops feet first towards the black hole. The smart astronaut stays inside the spaceship. So what's going to happen? Well, it's all due to tides. The closer you get to the black hole, the bigger tidal pull you feel, and that means your toes are going to be pulled more than your head because your toes are closer than your head, and you start to stretch out. The closer you get, the stretchier you get. So if you happen to be at this 3 solar mass black hole, 6,000 kilometers away here, you feel half a G on you, half a pull, and most people can survive half a G. You'd say, oh, there's no problem. When you're 2,000 kilometers away, 18 Gs, you're going to feel that. Human beings aren't made to withstand 18 Gs. In fact, the closer you get, the stretchier you get, you're going to break apart. Everything would break. Your bones would break, your skin would break, and you'd end up being little tiny pieces strung along of dumb astronaut pieces. When you're at the black hole, that 9 kilometers, 10 kilometers, you're just outside the Schwarzschild radius, it's 150 million Gs. And there's no way you can survive that. So you aren't going to survive getting there unless you were made out of some really fantastic rubber. So what happens? You have dumb astronaut spaghetti strings. The closer the astronaut gets, the dumb astronaut, the longer he gets, the more stretched out he gets. Here are just different pictures of a dumb astronaut getting closer and closer and closer. And well, you can think of it as spaghetti strings. And because we're astronomers, we like to name things. So we call this effect spaghettification. There's also an effect that as you, the dumb astronaut, your last little piece of your head enters the black hole, just as it enters, it's going to spew out a bright light. That's called the tube of toothpaste effect. Like you squeeze toothpaste and stuff comes out the top. You're squeezing the astronaut and a little piece comes out at the very end. That's called the tube of toothpaste effect. So spaghettification would happen to you. You would not survive. You die long before you got close to the Schwarzschild radius. Now, let's drop some things in a black hole just for fun. Let's drop these 4 items in. Do we know if we come by later that they're inside? That's a kind of, do we know or don't we know? Well, no. All information is lost at the event horizon. This white dotted line is the event horizon. All information is lost at the event horizon. This is called cosmic censorship. In other words, the singularity is at the center, and there can be no naked singularities. So Stephen Hawking, John Preskill, and Kip Thorne made a bet in 1991. I've got to read it because I don't want to mess up the legalities. In 1991, whereas Stephen Hawking firmly believes that naked singularities are an anathema and should be prohibited by the laws of classical physics, and whereas John Preskill and Kip Thorne regard naked singularities as quantum gravitational objects that might exist unclothed by horizons for all the universe to see. Therefore, Hawking offers, and Preskill Thorne accept, a wager with odds of 100 pounds sterling to 50 pounds sterling, that when any form of classical matter or field that is incapable of becoming singular in flat space-time is coupled to general relativity via the classical Einstein equations, the result can never be a naked singularity. The loser will award the winner with clothing to cover the winner's nakedness. The clothing is to be embroidered with a suitable concessionary message. And that was their bet in 1991. On February 5th, 1997, Hawking at a meeting gave in. He conceded. He said he gave Preskill a t-shirt, and the t-shirt said, "Nature abhors a naked singularity." So he actually said he lost that bet. So there maybe can be stuff leaking out or not. We don't know. So what can we do with all this? Not much. And if you're doing not much, you make up a rule. In 1967, they made up a rule that cosmic censorship leads to the rule black holes have no hair. If you've ever heard that rule, that black holes have no hair, it means that there's nothing to grab onto to tell you what's inside the black hole. The only thing you can measure is mass, spin, and charge. And most black holes are neutral, so they don't have a charge. So you measure mass, the gravitational pull of the mass, and the angular momentum, the spin. Cosmic censorship leads to black holes. Well, we're dealing with black holes, so there's always an exception. Stephen Hawking in 1974 showed that a black hole can actually radiate, lose energy, and slowly evaporate. It's going to take a long time. It's going to take longer than the universe will live for a 1 solar mass black hole to evaporate. And it's very, very faint. It's 1 billion trillion trillionth as bright as a 100-watt light bulb. Hawking radiation, it's called. Well, except, again, it's a black hole, so there's always an exception. This causes a paradox. Hawking radiation might violate the black holes have no hair rule, because Hawking radiation is carrying away information, but you can't do that. Black holes have no hair says you can't get any information out of a black hole. So Thorne and Hawking, Kip Thorne and Stephen Hawking, challenged John Preskill. Is information lost? They did this in 1997. Thorne and Hawking said no. Preskill said yes. And in 1997, Hawking conceded the bet. Thorne did not. And Hawking said he gave a T-shirt to Preskill and at a meeting. And so Hawking conceded, and it led to the black hole war. My battle with Stephen Hawking to make the world safe for quantum mechanics. There was a great to-do about this. Can information be carried away or not? Oops. Maybe. It means you have to combine quantum mechanics and general relativity. And quantum mechanics is the world of the very, very small. General relativity is the world of the very, very large. And nobody's been successful at really making one theory out of these two independent theories. It's a tough problem. Quantum fluctuations may allow Hawking radiation to carry away information. So in 2004, Hawking conceded the bet and Thorne did not. So Hawking said, yeah, maybe they're right. Maybe quantum mechanics will let you carry away information. So we've looked at a lot of the theory of this, these people who did, the theoretical physicists who built all this up. Let's see how we get reality here. How do we make black holes? If you want to make a black hole, stellar-sized black hole, what your birth weight is, your birth mass, matters, because when the star turns on, that's when it's born, turns on light, that's when it's born. The weight mass it has at birth determines its future trajectory in life. So if you're a lightweight star, like our sun is a lightweight star, you're just going to puff yourself out and become eventually a white dwarf and eventually cool off. Nothing exciting will happen. The Earth will go away, but nothing exciting will happen to the star. It just ends up as a white dwarf. If you're a middleweight star, that's heavier than our sun, more massive than our sun, say 3 times the mass of our sun or 4 times the mass of our sun, you explode. You end up by exploding and leave behind a neutron star, which is a really weird object. It's made out of neutrons. And that's odd, it just does odd things. If you're a massive heavyweight star, say 5, 6, 7 solar masses, you both explode and implode. The inside is so dense that it implodes and forms a black hole. So black holes are actually formed from heavyweight stars. And in general, they're more lightweight stars than middleweight stars, and more middleweight stars than heavyweight stars. So this is the most common star, is a lightweight star. So it's formed by stellar implosion, the black hole. A supermassive black hole is formed by taking a black hole and accreting other things onto it, colliding with a black hole, merging with a galaxy. And these guys have hundreds to billions of suns. That's how massive they are. Hundreds to billions of solar masses. And you find them at the one in the center of a galaxy. That's where we find supermassive black holes, in the center of a galaxy. So how many are there? The Milky Way, that's our home galaxy where our solar system lives, has about 100 billion stars, give or take. So that's 100 billion. Roughly 1 out of every 1,000 stars that form is massive enough to end as a black hole, because they're more lightweights than heavyweights. Therefore, our galaxy must have about 100 million stellar mass black holes. That's a lot. And there are perhaps 100 billion galaxies visible from Earth. If each one has about 100 million stellar mass black holes in it, and there are 100 billion of those galaxies, you've got a lot of black holes out there. 100 million times 100 billion, that's a lot. So when you ask how many are there are a lot of them. But currently, the closest black hole to us on Earth is 1,000 light years away. It's called HR 1869. That's its catalog name. Everybody's got a catalog name. It's a 3-star system with at least a 5 solar mass black hole in it. The lightest black hole is called Cygnus X3 in the constellation of Cygnus, and it's maybe between 2 and 4 solar masses. It's a binary star with the star V, a variable star, 1521 sig, and it's about 11,000 light years away. The heaviest black hole is OJ 287, which is a catalog number, and it's very, very distant. It's 3.5 gigalight years, 10 to the 9th light years away from us. And it's 1.8 times 10 to the 10th solar mass binary. It's 2 black holes orbiting each other in the center of this very distant quasar. That's the heaviest that we know of so far. So now what? We can make them. We can measure 3 things. How do we see them? And we see them with accretion disks. That's accretion disks. Some astronomers think accretion disks are where it's at. That's the important thing in life. An accretion disk is a swirling mass of gas and dust going around the black hole in the center and putting out a jet, a bipolar jet, a jet up and a jet down. And they're swirling disk of hot gas. And why do we know this? Because the hot gas, which is outside the horizon, event horizon, of course, the hot gas emits X-rays. And our X-ray satellites can measure them. They can detect them. They have. And the jets are visible in the radio. So supermassive black holes make supersized jets and supersized accretion disks. So how do you make an accretion disk? This is a little video that shows a neutron star going around a black hole. No music. And you see it begins to pull out a string of the neutron star. And it's building up an accretion disk. There's the accretion disk, it's built up as it begins to pull in all the material. So the first black hole that we think of, that we found, was called an X-ray binary star, Cygnus X1. It's 1 because it was the first. And it's a big blue giant star orbiting an unseen companion. And it was emitting X-rays. And it had a jet of hot plasma that they saw in radio. So it was emitting X-rays. It had an accretion disk. They think it was a black hole. The black hole has 15 solar masses. It's a heavy one, spinning 800 times a second, and it's 6,000 light years away from us. Well, this was the subject of another bet. In 1974, I got to read it again because it's legal. Whereas Stephen Hawking has such a large investment in general relativity and black holes and desires an insurance policy, and whereas Kip Thorne likes to live dangerously without an insurance policy, therefore be it resolved that Stephen Hawking bets 1 year's subscription to Penthouse as against Kip Thorne's wager of a 6-year subscription to Private Eye, that Cygnus X1 does not contain a black hole. Well, it turns out that over the years, evidence began to grow that it was a black hole, and Hawking finally said, I give up. He actually sent a year's subscription of Penthouse to Kip Thorne's home, where his wife would get it. And Kip Thorne's wife got kind of upset by this. But nonetheless, Stephen Hawking made good on his bet, but no money exchanged hands in any of these bets. Hawking conceded in 1988. This is a supermassive black hole, and this is a photograph of radio in the blue and red, and an optical picture of the galaxy Centaurus A. This is the galaxy. This is a dust lane through the center of the galaxy. And the black hole has a mass of 55 million solar masses. It's a supermassive black hole. The galaxy is 15 million light years away from us. That's not very far on the universe scale. And jets are 1 million light years long. These jets are 1 million light years long. So if you had radio eyes, well, I'm going to show you where this is. I have a little video from the European Space Agency. And this is the Atacama set of radio telescopes on the Atacama Desert in Chile. There are several radio telescopes that work together in the millimeter range of radio. And they actually took a picture of this. So if you want to see, if you had radio eyes, here's the moon, here are the radio telescopes, here are the jets. Look at that, a quarter of the sky. The jets reach out. That's because it's fairly close by. It's only 15 million light years, and they are 1 million light years long. And I think that's really impressive. The radio jet coming out of Centaurus A, so the supermassive black hole in the center here, is very impressive because the scale, this is the moon. I think that's really impressive. So what about our own Milky Way, the galaxy our solar system lives in? This doesn't have music, but let's move into Sagittarius. And as we get closer and closer and closer, it's going to show individual stars. This is not a simulation. This is real. They're getting closer and closer to the center of our galaxy. And eventually, things will turn kind of reddish because they're looking in the infrared now, not the optical. and they're going to look at a little square. See the little square? And the square is looking at individual stars. And that's reality. Those are real stars near the center of the Milky Way, and we think a supermassive black hole sits about there. So here is not a simulation. For 10 years, they followed these stars and plotted their orbit, plotted their path, and here they go. The black hole is here, and you see this star here. We now have completed a whole orbit for this particular star, and this is pretty well convincing that there's a black hole, because that's the kind of orbit it would get if it were going around a black hole. I can't, there. Black hole right there. And these are all the stars going about their orbits about the black hole. This is not a simulation. That's important to note. And the black hole in the center of our galaxy is 4 million suns. So black holes can also come in pairs. I mentioned OJ 287, and this is black holes orbiting each other in the center of this quasar. It's got 10 to the 10th suns, and it's 3 gigalight years distant, and they dance. What we're going to do is let these two black holes orbit each other. And the top row shows the black holes orbiting each other, and the bottom, the middle part shows the geometry of the space, and down at the bottom it's showing the sound waves, because the sound waves get closer and closer together, and so at the very end the sound waves make a chirp, because they're getting, then you won't hear them. That's not, there's no sound effects on here, but it's getting closer and closer. Whoops. So that was, I didn't mean to change the things, but that was the black holes merging. And
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery. On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma-ray burst was detected by NASA's orbiting Fermi Gamma-Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma-ray burst was unusually weak. Gamma-ray bursts are usually so strong that researchers assume that the gamma rays emerge from 2 back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma-ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
And that's, LIGO has detected merging black holes and merging neutron stars. So how much do we know? We know a little bit, especially about the outsides of black holes. We have a lot left to learn because we don't know much at all about the insides. However, we know we can actually photograph these things now, take pictures, and we can indirectly detect them. And it's still beautiful. So thank you very much for listening in on Black Holes Can Dance.